Okay, so this video is for the year 11 triple, and we're going to do our last sort of calculation topic, which is moments, and this is nowhere near as hard as suvat and momentum, so this is a nice one. I've left this till later because we wanted to do the hard stuff first. So, moment is a turning effect of a force around a fixed point called a pivot. For example, this could be the door opening around a fixed hinge or a spanner turning. So the way I like to think of it, you know, your door handle, you've got that pivot right in the middle. Well, to turn that without the handle would be really hard. The longer the handle would be, the easier it is to open that door. So just think of door handles when we think of moments. Now, the size of the moment depends on two factors. The size of the force applied, so how much force you apply to when you're opening the door, how strong you are, and the distance from the pivot. So the longer the handle, the easier it will be to open. And I've just put the perpendicular just means right angles. So if something, if we've got a straight line there, it's going to be a right angle. So this is perpendicular there. So, moments. This explains why less force is needed to open a door by pushing at the side furthest from the hinge than the side closest to the hinge. The push on the hinge side of the door requires more force to be exerted. So if you're trying to close a door, it's easier to close a door right at the edge of the door rather than by the hinge, okay, because of that distance from the pivot. The pivot meaning where the door is hung. So, this is what we really need to get into now. You'll find this at the front of your books, at your front of your exams, and I'll show you where now. So M, capital M, represents momentum. The capital F represents force, and your distance there, lowercase d. And we've got what they all mean. So Newton meter, because it's an FD, it's a force times your distance. So it's a Newton meter, not a Newton per meter. Sometimes you'll have a Newton centimetre, depending on what units we're dealing with. More often than not, we try to get it to meters, so just be aware of that, especially with the questions coming up. And like I said, at the front of your book, at the front of your exam, you're going to find this. It's the last one, so momentum equals force times distance. You don't really have to remember this. You just need to know how to use it, okay? All right. So straight in with the examples here. A spanner is used to undo a nut. A force of 25 newtons is applied at the end of a spanner, which is 10 centimeters away. Calculate the moment when the spanner is horizontal. So a fairly easy calculation here. I don't know if you want to go and try this. Press pause, and then we'll have a look. So we need to calculate for momentum, because it's I keep saying momentum. We're going to calculate for a moment. So M equals, well, F is next to D, so F D. So now I just need to know what my force is. Well, my force is 25, so it's 25 times your 10 centimeters. Now you can convert that to 0.1. And then we'll have a Newton meter, or I'll do it this way. So 25 times 10 is going to give me 250, and this is going to be a Newton centimeter, because this is centimeters. If we wanted to convert that to meters, then we could either do it this stage, where you'd put 0.1 as your meter, or we can do it at this stage, and we can just move the decimals back. So this is going to be 2.5. There, Newton meters. Sorry, I should have done that. Okay, so that is way too easy. So they're not going to come up like that, obviously. So let's push on now. There's my workings there. If you just wanted to have a look at that, so I've done that before. Balancing moments is what we really need to do, and just like with momentum, one side equals the other side. So the sum of clockwise moments, so clockwise, is going to equal the sum of the anti-clockwise moments. And I'll show you what this means. So if you think of when you're on a seesaw, if you get a person so these two people, by here are both 50 pounds, and they sat at the same distance, therefore they equal the balance. So that is balanced. But sometimes, if I go on with my kids sometimes, my kids need to sit right at the end, and I will have to sit sort of further in because I'm heavier, to just balance that. If I sat right at the end, this whole seesaw would just come down and it wouldn't move. So I need to sit sort of further in. So the more mass you have, the further in you've got to come to balance this pivot. So the person on the right exerts a force downwards, the person on the left exerts a force downwards. So I would usually, when I see a diagram like this, just to remind myself now, you need to know that this way is clock and this way is anti-clock. Okay? So that's just the first thing we need to be aware of now when we're coming to balance these things, that if it's going this way, down, that's clockwise. 1, 2, 3, 4, just like a clock. And then this way would be maybe, what would it be by here? 8, 9, 10, 11. So it's going against the numbers here. It's going from 11, 10, 9, 8. So it's going anti-clockwise. It's going down like that. Okay? Just a little bit more then on if people are identical weights. So you can read that if you want, but the calculations that we're more interested in. So I'm going to just show you an example now. So this is a typical example. Calculate this is required for a perfect balance. So I've got a mass there, and it's not telling me the mass, but it's telling me there is 7 newtons. Now, think back as well. I don't know if you've done this with Mr. Jeeves yet, but the gravity times your mass is going to give you that weight, which is measured in newtons, and that is important later on. Okay, so we'll be dealing with this later on, but this time it's done for us. It's just telling us there's a force of 7 there, because it's quite light. This is a bit heavier, so it's got a force of 18. Now, this distance, okay, from the pivot is 16 meters, and we don't know the distance here. So how are we going to work that distance out? Well, the first thing we would do is just to remind ourselves that a moment equals force times distance. And then I would probably, if this was in the exam now, I would probably, because it's not gonna come up as clear as this, I would probably sketch a little diagram of this, but I'm not going to in this case. But if you're following at home, I would recommend maybe to get this diagram down. It won't take long. You literally do a line, you do a little pivot, 2 circles, one bigger than the other. You do a distance from the center there. You'd say 16 meters. You'd say 7 newtons. We'd say 18 newtons there. We don't know this one. Okay, so it didn't take long. So from earlier, we know that, and I'll just show you. No, I can't do that because I'm recording. From earlier, we know that an anti-clockwise equals the clockwise moment. So this is going to equal this. So just like we would with momentum, we're going to calculate each side, and then we are going to solve. So I'm going to use my moment equals force times distance to calculate the anti-clockwise side. So what is my force? Well, it's 7 times, what's my distance? It is 16. 7 times 16 is going to equal, what's my force? 18. What is my distance? I don't know. So I could call that x. So I'm going to say 18x. And it's just a case now of solving and simplifying. So I think 7 times 16 is 112 equals 18x. So that's my first step. And then I need to divide both sides by 18 to get rid of my 18 on this side. So I would 112 over 18 equals x. And then I would solve, so x equals around about 6.2. What's my units? Well, we're still in meters and we're still in newtons, so it's a Newton meter. So that is a Newton meter. And that's one example then for you. I'm going to push on to the next example now. which is calculate the force required for a perfect balance. And if you want to press pause by here, maybe try it. This time we've got two distances, this time in centimeters. We've got a force by here, but we've got an unknown force here. And if you want to try this, press pause. If not, I'm going to do the workings out right now. So I'm not going to draw the diagram this time. I'm just going to remind myself of the formula. And this can be found right at the bottom on page 2. M equals FD. Then I know the anti-clockwise moment is equal to the clockwise moment. So this is going to equal this. Okay. So let's do my anti-clockwise. Well, what is my force? I don't know. It's Xn. I'm going to leave that a minute because I'll show you. If you start writing it like this, X 162, it gets a little bit. Well, it doesn't look right. So I'm going to put my distance first, which is 162, and then my unknown 162x equals. I'll probably put the distance first as well here. 63 times 3.5. Okay. Then we're dealing with centimeters now. I could easily convert that as well. So I might convert that now. I might do the conversion. So I'm going to convert this centimeters to meters now. So that is just divided by 100 because it's 100 centimeters. 1.62x equals 6. No, it's going to be 0.63, isn't it? Of course. So that's 0.63 times 3.5. Now I can solve. So I can solve for this side. 0.63 times 3.5 is going to give me 2.205. And then 1.62x. Now to get x on its own, I need to divide both sides by 1.62. So x now becomes 2.205 divided by 1.62. So x equals 1.36. Now, because I converted at this point to meters, I'm going to keep it as a Newton meter. But you can also think that x could have been 136 Newton centimeters also. Okay, so just be aware these units can be interchangeable there. So centimeters, Newton meters, Newton centimeters could also be Newton centimeters as well. So that's that problem. Maybe now you could have a go. The next one, so that was that last one. Example 3 now. Oof, or maybe not actually, because now we are 5 kilograms. Unknown newtons, 4 kilograms. Unknown distance there. So what are we going to do here? So this one I've worked out beforehand because there's a couple of steps. The first thing we need to do is to read the question. Calculate the distance required for a perfect balance. The acceleration due to gravity is 10 meters per second squared. Now I know that gravity is 10. It's probably going to be 9.8 for you guys in your exam because they like to get it more accurate, more precise. But for this one, it's nice and easy. Now, in the front of your books as well on page 2, I hope this continues to record now because I'm changing. Now we've just shown a formula sheet, so I don't know if that's picked up. Yeah, I think it is. We're on 1 minute, yeah. So the formula sheet showed me that weight equals mg, mass times gravity. Well, our gravity is 10 meters per second squared, it's acceleration, and our mass is going to be 5 and 4. So I'm just going to show you on the next page how I work this out. We've got now. So then, I've drawn my diagram. Okay, I've done my 10 meters there, my 5 kilograms, my unknown meters there, my 4 kilograms there. I'm sorry that it's not that clear. So I've gone and done my anti-clock equals my clock. Now I've wrapped this equation up. So 5 times 10 is my mass times gravity there. Remember, weight equals mass times gravity. So mass would be 5. My gravity due to acceleration. Now don't get confused, because that 10 is not that 10 there. This 10 is that 10 there. This 10 is due to gravity. So 5 times 10 is going to be 50 times 10 there. It's going to be 500. This side, I've got 4 times 10. My 4, my mass there. My 10 has also come from gravity. So acceleration due to gravity, which is 10 meters per second squared. And then that's the unknown. And then I've just worked out as following. So it comes to be, at the end, by the time I do it all, 500 over 40, because I've got 40x, get x on its own, I divided both sides by 40, and x comes out to be 12.5 meters, because we're dealing with a distance there. So it's not going to be Newton meters. So then, now that we've had a chance to practice, maybe it's time to... We've got this. Let me zoom in on that. So your weight equals mass times gravity field strength, gravitational field strength. So W equals mg. Now I'm afraid that this, when I go back, have a couple of questions. So I'm going to tell you how to answer these questions, because sometimes we have problems uploading work to Teams. So I'm going to try and keep it as simple as possible. How will I know that you've done it? Well, I want you to either write the answer in the comment section with your initials on YouTube. For example, my name's Kevin Timothy, so I'm going to put KT, and that's going to be question 1 equals the answer going. So I'm going to give you an option of 4 answers each question, and you're going to work them out, and you're going to tell me which one suits it. So question 1 would equal A, question 2 would equal B, C, 4, and so on. There's 4 questions in total. Your question 4 is the challenge question. And then you simply give me the letter of whichever one you think it is. Now, if you're not comfortable with people seeing your answers on YouTube, just send me an email. You can use one of these. I prefer the second one, kmt@cantonian.cardiff, because I check it more regularly, because this one is not sort of set up yet. I mean, I do check it, but not as often as this one, because it comes straight through on my iPad. So if you want to be sure that I get it, kmt@cantonian.cardiff. Or you can submit your answers direct to Teams, okay, under the comment section on where the Teams assignment is. If you want to take photos of your work and upload it as you were before, you can still do that. I just need to see some evidence, and I need to see your initials to see that you've done it, okay, to get your mark on Teams. So I'm going to go ahead and show you the questions now. By all means, pause on each one. And they're very, very similar to the examples. So if you're still not sure what's happening, go back and watch the examples that I've done. And also maybe watch some videos on moments yourself, because there other people may explain it way, way better than me. Okay. So here's question 1. Calculate the distance required for a perfect balance. Again, it's very similar to our first question. Follow the method, and one of these is the correct answer. Question 2. Calculate the force required for a perfect balance. This time there's a force unknown. This one could be one of these answers. Well, it is one of those answers. Question 3 coming up. Calculate the distance required for a perfect balance. The acceleration due to gravity is 10 meters per squared. It's getting slightly harder now. That was question 3. And then question 4, your challenge. I'm going to throw something a little bit new in here. This time I've got 2 people, 2 masses sat at the end. What are we going to do about that? I wonder. Okay, that's why it's a challenge question. I'd like you to problem solve this. Okay, thanks so much for your time. Hopefully you've got something out of this video, and I look forward to seeing the answers come through. Have a good day.